So this is my Lab 2 presentation for circuits for Physics 2 and with Dr. Zabel. So the purpose of this lab is to measure and predict circuit behavior by using multimeter readings, and we do this by doing a series and parallel resistor circuits and measuring the current within the circuits that we create in lab. So the fundamental principles that we have for this lab is the node rule, which states that the total current entering node is equivalent to the total current leaving it, and I just have that represented in a summation. Ohm's law, which describes the relationship between voltage, current, and resistance, which is V equals IR, and the loop rule, which means that in a closed loop circuit, the sum of the potential differences must equal zero, and I have that represented in a summation as well. So predictions for current 1 and current 2, we predict that both current 1 and current 2 will be 0.02 amps because since the current is the same everywhere in the circuit, we use Ohm's law. So we got the number 3 volts by summing the two batteries of 1.5 on the left, as you can see right here. And then we got the resistance by adding 47 and 100, which is 147 ohms. So that's how we calculated it using Ohm's law. I'm getting a value of 0.02 amps. So this is a physical picture of our experiment set up in lab, and the system is the circuit and the surroundings is everything else. So the result of this lab showed that the node and the loop rule proved to be correct throughout the entire experiment. And just to kind of elaborate on that, the steps that we did were we constructed a circuit using two resistors, two ammeters, and two batteries in series, with the first current equal to 17.5 milliamps, the second current equal to 17.3 milliamps, and for the second step, we reverse the position of one ammeter, with the second current being being negative 17.5 milliamps, and nothing relatively changed. So for the third step, we replaced an ammeter with a voltmeter, and we had a value of 1.107 for the ammeter, 2.5 for the voltmeter, which had a sum of approximately 3, which makes sense because the voltage is 3 volts. So then we connected the battery to the bulb with the capacitor in series, and the bulb got dimmer faster in approximately 4 seconds. And once we disconnected the battery, the bulb was bright and dimmed in approximately 12 seconds. So we repeated the process with the other bulb, with the bulb getting dimmer but a little slower at approximately 14.78 seconds, and the bulb being bright at first and slowly dimming at around 38 seconds total. So we only see voltage differences between the batteries and the resistors. So from A to B, we see negative 1.5 volts, and then the 47 ohm resistor from C to D is approximately negative 0.95 volts, and then the resistor of 100 ohms from E to F is approximately 2 volts. So using the loop rule, we summed all the volts together, and that should approximately equal 0 volts. And a note that we can also use the node rule to find this as well. So using the resistance graph, we can see that when there's a higher resistance, the slope of the drop is higher, and when this also makes sense because with the battery from A to B, we show a voltage gain. So using the round trip potential plot, I just plotted this using Google Sheets. It shows a linear and decreasing relationship. I know it shows a increasing one, but if you just switch the X and Y axes, it shows a linear and decreasing relationship. And we did this by using the time and the volts and then using the ln of the initial and the recorded voltage. So assumptions and potential errors we can have for this lab is that an human error in recording the time completely accurately, placing the circuits in different positions, and assuming that our circuit is representative of real world conditions. So answering the what if question, if you charge a capacitor with no resistor in the circuit, how quickly would our ideal model predict the capacitor in full charge, and would this prediction happen in real life? So in an ideal model, the capacitor without the resistor would have the capacitor instantly charged, but this would probably not happen in real life because there will never be exactly zero resistance. So the second part is to use an ammeter to measure how long it takes. So in our lab, it showed that it took around 4 seconds for the capacitor to charge, and this is different than the predicted time because, as already stated, there will never be a zero resistance in reality. And thank you for watching my presentation, and have a good day.